Welcome to The Explainer. Today, we're diving into a breakthrough that could literally rewire how AI works. It's a new way for neural networks to remember things that could make them faster, way more powerful, and, surprisingly, a lot more like our own brains. So, think about how you remember something. It doesn't slowly buffer and load, right? A lot of the time, a memory just snaps into place. But for AI, it's always been this slower, more deliberate process. So, what if we could change that? What if an AI could pull up information with that same sudden, lightning fast efficiency that our own minds seem to have? Well, an international research team might have just found a way to do exactly that.
Okay, so let's get into it. To really understand why this new discovery is such a huge deal, we first have to talk about this massive wall, this huge problem that scientists have been slamming into when they try to build AI that's more like a brain.
And it all comes down to this idea of higher order interactions. See, most of our current AI networks are pretty simple. They tend to look at connections between two neurons at a time, just one-to-one pairs. But our brains, oh, they're so much more complex. They're like a symphony with whole sections, whole groups of neurons all firing together to create a single thought or memory. It's that group behavior, that collective action, that's the real secret sauce. And here's the catch. If you actually try to model all of those possible group interactions, every trio, every quartet, every possible combination of neurons, the numbers just get insane. The amount of computing power you need explodes exponentially. They call it a combinatorial explosion, and it has been a fundamental roadblock holding AI back for years.
So how in the world do you solve a problem that seems mathematically impossible? Well, you don't play by the old rules. You change the game entirely. And this research team found an incredibly elegant solution by, and I mean this literally, thinking in a completely different shape.
And this slide just lays it out perfectly. On the left, you've got your classic networks, stuck in that one-to-one rut. But on the right, this is the new stuff, curved neural networks. Instead of trying to calculate an infinite number of connections, they changed the underlying math itself. They basically put the whole network into a curved statistical space. And this one geometric trick, this one change, allows the network to handle interactions of all sizes, all at once, with just a single new parameter. It's an absolutely genius way to just sidestep that whole combinatorial explosion problem. You know, it's a big deal when the researchers themselves sound a little surprised by it. As the lead researcher, Hideki Shimazaki, said, it all started with this one simple idea. And it led to something they never expected. This wasn't just some small improvement. It totally changed how the network behaved, and that led them to some incredible discoveries. And really, these discoveries are what it's all about. This new model wasn't just a little bit better. It uncovered 3 totally new, really powerful ways that an AI can actually work. Okay, first up, and this one is just wild, is explosive memory retrieval. A normal network kind of slowly works its way toward an answer. But this new model, it does something called an abrupt phase transition. It literally snaps from a messy, disorganized state straight into a perfectly clear, stable memory. It's sudden, it's decisive, and it sounds a lot like that human aha moment we all have when we suddenly remember something. So, how does it do that? How does it make that snap happen? Well, the second discovery is the secret sauce behind that explosion. It's a process they're calling self-regulating annealing, which is basically a super smart way for the system to guide itself to the right answer, fast. Researcher Fernando E. Rosas explains it's a bit like a process called simulated annealing, where you cool a system down to find its most stable state. But here's the twist. The network cleverly controls its own temperature. As it gets closer to the right memory, which is a low energy state, its own internal temperature automatically drops. That reduces all the random noise and forces it to lock onto the solution even faster. It's this awesome feedback loop that drives that explosive snap we were talking about. And the third discovery? Well, this is where things get really practical. Because this explosive self-guiding system isn't just faster, it can also store way more information and more reliably than the old models. It massively boosts the network's total memory capacity. And you don't have to take my word for it, the results speak for themselves. They tested this on a big data set of images. The classical model did okay, moderate success. But the new curved model, a significantly higher success rate. This isn't just a theory. You can actually measure the jump in performance. It just works better. Okay, so what does this all mean? We have this faster, denser, more brain-like memory. How is that actually going to shape the next generation of AI that we'll be interacting with every day? The potential here is just massive. The researchers are pointing straight at improving the generative AIs we're all using. Think about it. Imagine an AI writing a story. With this kind of memory, it could perfectly recall a tiny, subtle detail about a character from chapter 1 and bring it back in a meaningful way in chapter 20. That kind of long-term coherence is the holy grail. For generating images, it could lead to much more logical and complex scenes. Beyond that, this could create more energy-efficient AI and even give neuroscientists a brand new tool for understanding the amazing complexity of our own brains.
And that's really the big takeaway here. As researcher Miguel Aguilera puts it, this isn't just about a clever engineering trick. This is a huge clue, a big step forward in understanding the very nature of information itself, how it's stored and retrieved in any complex system, whether that system is made of silicon chips or living neurons.
And that just leaves us with this one fascinating question to think about. As we build AI that starts to mirror the incredible, explosive efficiency of the human brain, well, those old, clear lines we used to draw start to get pretty blurry, don't they? This kind of research doesn't just give us better technology. It really pushes us to rethink what intelligence even is, no matter where we find it.